In this lesson, we're going to investigate the distance that a space shuttle travels during its ascent phase into space. And so, what better way than to get excited about doing a problem like this than actually checking out some specific information related to a shuttle launch and watching that shuttle launch at the same time. There's really nothing quite like a rocket as it ascends into space. And so, in your picture here, you've got a shuttle launch and you've got a Google map of actual data from a specific shuttle launch. And these two things, the actual launch you're watching and the data, might not match up perfectly, but a lot of these things are going to follow the same trajectories. So we're going to watch the shuttle launch here. We're going to see the path that the shuttle takes as it goes into space. Then you can see some different things here on Google Earth. Okay, MECO is going to be main engine cutoff. ET separation is the external tank separating. And it shows you about where these events happen as the shuttle is launched. And the problem that we want to investigate is what's going on to the space shuttle during that ascent phase. How much altitude does it acquire over the first 480 seconds? So using a TI Inspire and some data from TI Exchange website, I am going to create a scatter plot of the velocity versus the time, or time versus velocity. And we're going to create this scatter plot and look at the velocity equation that we get when we do a regression. So I'm going to plug all this in right now into the TI Inspire, and you can see it's moving along pretty quickly. And if you need to slow it down to see exactly what's happening, that's fine also. But time is going to be there in list 1. You can actually label it time. Velocity is going to be in list 2. You can actually label that velocity, and that'll be really important later as we start to develop the scatter plot of this information. Okay, so I'm taking the chart on the right, I'm plugging it into the calculator on the left, and we're just going to let my fingers do the walking real quick here. It just takes one more second. Okay, now we've got all the data in. So we've got the velocity at specific times. All of this is going to be in meters per second. And so what we're going to do is we're going to create a scatter plot of this information, a regression formula. We want to figure out what equation best represents all of that data. Okay, and I happen to have worked this problem out previously, and there's different ways that you can do it, but I happen to know for a fact that the cubic regression model will give us our very best fit. And you can explore different regression models, quadratic and quartic and other different regression models to find out which ones work. All you need to do is tell your X list to be time, tell your Y list to be velocity, and then just store all that information. Now, if you're looking at your screen like I am, you won't see the entire equation because of the way that the list is set up, and that's okay. The list is actually gives us that equation. It's at the very top of our calculator screen. But what we're going to do is we're going to open a new slide and we're going to graph that equation. Okay, so to open a new slide, it's just Control I on Inspire, open your new slide, and then we're going to monkey around a little bit with the window because I want to be able to see a good representation of this graph. And again, I'm using some settings that I know will work because I've played with it just a little bit. And if you're discovering this for the first time, you get to explore these settings. Which ones show you a good piece of the graph? Which ones don't? And how can we tell? And so I know that on my scatter plot for the X values, I went out to 480. So I'm going to go 500. And I know for the Y values, I was booking along really quick. So I picked 5,000 to start. We can always change these. And in fact, I do here in just a minute. Okay. And so what we're going to do now is add the scatter plot part. And that's the actual points that we put in. And with the Inspire, you can just tell list 1, the X list, hey, we want that to be time. You can tell the Y list, hey, we want this to be velocity. Don't hit enter. Go ahead and arrow key down first and then choose enter. And it will give you a scatter plot. And you'll see that the scatter plot actually matches up really, really, really well with a cubic equation. So here it comes. Boom. It's almost a perfect fit. It's almost a perfect fit. Now what I'm going to do is I'm going to do what's called a zoom stat window or zoom data. And this actually gets us the best window for the data that we put in from our list, okay? I'm going to move the equation up so that you can see it a little bit better. So here's our regression equation. It's a cubic, okay? It's a cubic equation. So let's figure out the distance traveled by the space shuttle using that cubic equation. Well, think about a train moving at 60 miles an hour for 4 hours, okay? Moves at a consistent rate. It's just going to be distance equals rate times time. So it's going to be 60 miles per hour times 4 hours. The hours cancel, you get 240 miles. Or we could graph this. So if I graph this, what I'm looking at is a graph where my x-axis would be the time axis, my y-axis would be the velocity axis, and this is really bad handwriting, sorry. And so my velocity is 60 miles an hour. So I'm just going to draw a horizontal line about where 60 would be. Okay, there it is. And then I want to know how far have I traveled over 4 hours? Well, I can make a vertical line to represent my 4 hours. I start at 0, I stop at 4, and looky here. I'm going to find the area of this rectangle right here. Well, it's the exact same thing that we discovered, that we remembered right above. Okay, distance, rate, and time. 60 times 4, we get the same thing looking at a graph, okay? 4 times 60 is the area of the rectangle. We're talking about miles covered. Well, we can apply this same thing to the space shuttle. And when we get to the space shuttle now, we're talking about, though, a velocity that's changing, okay? And so to handle that, we're going to do what's called an integral. Well, here we go. With integrals, back to our train problem, we can go from 0 to 4. And what this is going to do is give us the area under the curve. Well, we know that we're traveling at 60 miles per hour. If I integrate this, I get 60t. All right, I'm going to evaluate it from 0 to 4. And so when I do that, I'm going to have 60 times 4 minus 60 times 0. This will give us the area under the curve, which is the exact same thing that we saw just 1 second ago when we graphed it. It's going to be 240. Okay. Well, how does that work with our space shuttle? This allows us, integrating allows us to find the distance covered by the space shuttle vertically over the first 480 seconds of flight, and it allows us to use the equation that we found the regression for. Okay, so here comes that equation in case you couldn't see it when it came by the first time. All right, it's going to be, and this is 6.9 times 10 to the negative fourth. I went ahead and put all the decimals in because it's easier for me to work it out that way. So here we've got this equation, and what we want to do is we want to find the area under this curve. This is our velocity equation. And if we integrate velocity, we get position. So this will tell us where we're at in position relative to time. It will also tell us how far we've gone from 0 to 480 seconds. So what I'm going to do is I'm just going to follow my rules of integration. I'm going to integrate this, and I'm going to evaluate it from 0 to 480. And remember, for this, and watch, for this particular problem, when we evaluate from 0 to 480, there's actually going to be that 0 will be that whole second term, okay? So here we go. All right, so when you use your standard rules of integration, all you do is you add 1 to that exponent and divide by your new exponent, okay? The constant, the coefficient in front doesn't change at all. So I'm going to end up with this long decimally times t to the fourth divided by 4. That's my new stuff, okay? 0.03t cubed divided by 3 plus 13t squared divided by 2 minus 103t. And we're going to evaluate that from 0 to 480. And with the help of my trusty calculator, I'm going to go ahead and punch it in because that's a lot to carry in my head. But basically what you're going to do is everywhere that you have t, you're going to substitute 480 in its place. Minus, and then everywhere you have t, you're going to substitute 0 in its place. Well, notice that all 4 terms have t. So t being 0, 0 times anything is just 0. Okay? Make your substitutions here. You're probably going to want to use a calculator to double check your math. Go ahead and do that right now. And what you're going to discover after you do this is the amount of meters of distance that the space shuttle covered during the first 480 seconds of flight. And these are vertical meters, not necessarily horizontal. Okay? So there you go. There's the whole problem right there. I'm going to punch it into my calculator, and I get this big, huge number. All right, that's the number of meters, okay? 1,263,750.176 meters. That's a lot of meters, okay? And, you know, living in the United States, I don't do a lot with meters, so it's not necessarily as user-friendly to me as maybe feet would be. So if I remember that 1 meter is equal to 3.28084 feet, that'll help me, okay? So I'm just going to convert this. I'm going to take all my meters and divide them by 3.28084, and this should give me how many feet I've gone. And again, I'm going to punch this into a calculator because I want to make sure that I get things correct. You know, it can be a little tricky sometimes with unit conversion. And when I do that, I end up with still a really large number. And again, when I'm working with feet, once I get above a certain number of feet, I feel uncomfortable because now I'm more comfortable with miles. So when I punch this guy in, I get 385,038.64 feet. That's a lot of feet. And so since it's more than like 100 feet, I want to know how many miles I've gone because I get miles. So what I'm going to do is I'm just going to take this number, this 338,038.64 feet. I'm going to divide it by the number of feet in a mile. That'll get me my miles. So that's 5,280. And when I punch that into my calculator, I get 72.9 miles. And so using the data that I got from NASA, using some calculus and some physics in there with rate and time and all that, I can determine about what the altitude of the space shuttle will be during its launch phase around the 480-second mark. Now, this may or may not be super accurate according to NASA's stuff. They've got really fancy calculators that can do all that math for them. But this is going to be really, really close to ballpark. And I think if you look at the data for this particular flight that I'm investigating here, the actual altitude is something like 65 miles or something like that. So we're really, really close using approximations. And when you're trying to figure out the distance of a shuttle launch, I didn't carry through a ton of decimal places here at any point in this problem. And sometimes that helps as well. The more decimal places you have, the much more accurate information you're going to get back out. So using this information now and maybe using the spreadsheets from the beginning, go ahead and punch some different regression formulas into your calculator and find out, is this the actual best velocity regression to use? What about acceleration? What about position? Remember, all of those are related. So if I have a position function and I take derivative, I can get velocity. And if I take derivative of velocity, I can get acceleration. Then I can go backwards. If I have acceleration and integrate that, I get velocity. And if I integrate velocity, I can get position. And if I have known times for all of those, then I can find out exactly how fast I'm going, how far I've gone, and how quick I'm doing it. So this is a really cool problem to do. Enjoy it. Try finding the perfect fit. There's more to do. This is just an introduction to that. I hope you've enjoyed working this problem out with me. This is one of several, and please feel free to tweet me at Hazelwood Math anytime with any other problems that you may be interested in or need some help with. I'd love to be able to help you. You can also follow me on my YouTube channel, youtube.com/HazelwoodMath. Or you can search me out on nomia.com. Just look for the profile, Scott Hazelwood.